Hey guys, welcome back to AlgoYogi. We are doing graph series and our next problem in the list is number of provinces. So let's go to LeetCode. There it is. There are n cities. Some of them are connected while others are not. If city A is connected directly to city B and city B is connected directly to city C, then city A is connected indirectly to city C. Now a province is a group of directly or indirectly connected cities and no other cities outside of the group that's given to you. Now you are given an n cross n matrix called is connected, where basically the value at I and j position in the grid, if it has 1, that means those two cities are connected. If it's a 0, that means those two cities are not connected. This is called adjacency matrix. We have worked with adjacency list a lot. We create it ourselves, but this time it's already given to us as adjacency matrix that represents the connection between these different nodes. This is also one of the ways a graph is stored. If you have studied graph theory, you would know about it. So, and I think it's one of the best ways to basically traverse through a graph and see like what are the connected nodes. Now we need to return the total number of provinces. Easy peasy. It's a problem of counting connected components. That's it. All right, so I have taken this example, which is also the first example there. Now this is the adjacency matrix called is connected, so we can just name it. That's is connected. And by the way, this will be given here as a 0, 1, 2, but I have just written, to match the name of the node, because we are given 3 nodes, 1, 2, and 3. That's the number of nodes given to us. And this represents basically the value here. 1 means 1 is connected to itself. Well, 1 is connected to itself. 2 is connected to itself. So you would see that the diagonal is always basically 1. Because a node is connected to itself always. So what we're going to do is we will start traversing our graph, and we will be basically traversing. Let me move this thing right here. So what I can do is I can run a DFS. How do we count connected number of components in a graph? Is basically you start iterating over the graph. You start visiting maybe from 1 to n minus 1 or 0 to n minus 1, I think. And then you basically, when you're visiting one node, then you visit all the connected nodes to that particular node, put it in the visited set. And then once you start visiting another nodes, before doing that, you basically increment the number of, you can say, provinces in this case that you just found. So we'll have basically a for loop. So we'll have a for loop, and let's call it u in length, we can say, in this case we'll say range n. All right, and then we can just provide it basically we can send in u plus 1 in this case, because our graph is kind of starting. Actually, yeah, we don't have to, because we can just consider this 1 is actually 0, 2 is 1, and 3 is 2. Simple. This doesn't really mean, because indexes at the end of the day, I really wish they had given to us starting with 0, although it doesn't matter. So 0, 1, 2, 0, 1, 2. This is a better. So then we can just send in this u to our DFS, but only when if u not in visited. If it's not in visited, then I'm gonna call DFS on it, and let's send this graph inside, and then I'll have a variable called let's say provinces, initially 0, and then I will just increment it, provinces plus equals 1, and then in the end I will just return this. So return provinces. All right, so how would our DFS look like? So let me move this even further. So this will be my DFS. So DFS will be taking U, right? And then now for all the connected connected nodes to my U, how do I find those nodes? So for, let's say, V in range N, if this V not in visited and this V basically in my grid, I can say, or is connected right here. So this U and V is equals to 1. That means these two are connected. So what I can do is I can run DFS on V as well. So this will V is basically you can say a connected node to itself. It's neighbor of U. So that's why I will run DFS on V, so that I mark this U also visited. So what I would do is, what we are actually missing is, we can add this right here, this U right here. So visited dot add this U. All right, so that will be the entire code. Super simple, and I've just written it for us. You can just go ahead and like write it line by line, and that's it. Voila. Let me also write my code. All right, so as I said, I will have my N calculated, which is the length of my number of nodes basically. So I'll say len is connected. Now for U in range, I will send it this N, and then I will basically call my DFS. But we forgot to have a visited set. So visited will be a set empty in the beginning, and if U not in visited, if this is not in visited, then I can basically call DFS on U, and then I can increment number of provinces. All right, so I can just say provinces will be initially 0, and then I can just increment it each time by 1 if U is not in visited. All right, now what we can do is let's just write our DFS. DFS will take U, and because we are at U, so let's add it to my visit set. So visited dot add, and I'm visiting basically U, but let's also visit all the neighbors of U, so which will be also, these neighbors will be in the range of a number of nodes, so which is N. And if we not in visited, and also in my is connected, basically at U is where I started already this. So for this U, and in my is connected grid, if the position U and V is equals to 1, that means they are connected. These two nodes are connected. That means they are part of this one provinces or one connected component. So that's why I will actually go ahead and visit everything in V as well, and not just V, all the neighbors of V as well. So I'll call DFS on V, and I think that will be it actually for our DFS. Finally, I can basically return the number of provinces right here, and let's zoom out and see if this passes our test cases. Yes, it does, and that's like exact code that we wrote as a pseudocode. We've just like translated it like line by line, and voila. So let's talk about the time complexity. Time complexity here would be actually n square, and the reason is you are visiting using these 2 for loops at max. You are visiting all the nodes. So n into n, that will be the time complexity. Although it seems like you're running a for loop on n, so n into this DFS is actually also at max will be kind of like iterating, not iterating, running the recursion over all the other remaining nodes for all the u. So it will be actually for u number of times it's iterating over v number of nodes. So u and v, they are both equal. If you remember, this u and v are in the range of n, so n square is the time complexity. Space complexity will also be big of n square, and that's because we have this visited set that actually stores all the nodes. Actually all the nodes, then that means n, because at max it is storing just all the nodes, right? Yeah, that's the number of nodes, so it will be actually n. So this is the space complexity, and time complexity is n square. Let's go back to AlgoYogi, mark this problem solved, and I think these three problems were very, very similar. They were all about counting the connected components, but there were minor differences, of course. Enclosed islands is basically just the island has to be closed by water, and the boundaries are not considered. You're just counting the number of connected components. In number of enclaves, you were following the same logic, that you are not considering any land that's on the border, only what is actually inside, surrounded by the water, that piece of land. But you were also counting the number of land cells that particular connected component contains. So that was right here, and number of provinces is basically just simple connected components, and yet they just gave us the adjacency matrix. So that was the only difference, and we didn't need to create the adjacency list from adjacency matrix, because you can of course just run over the range and then check if there is one present between the intersection of two different nodes. That means they are connected. All right, so see you guys later in the next problem. Bye bye.